So in this video, I'm going to be going over this problem that is on Taylor series, Taylor polynomials, Taylor's inequality. This problem appeared on a final exam given at MIT. And actually, this is a very typical leveled problem. Okay, so with that expectation set, let's begin. This first part asks to find the Taylor series of ln of 1 plus x centered at a equals 0. So immediately I'm thinking, I don't want to take derivatives of this and find the brute force method because it's going to get messy and the pattern might be hard to find. Okay? Instead, I know that the derivative of ln of 1 plus x, the function in question, is 1 over 1 plus x. Okay? This I can easily find the power series representation of, because 1 over 1 plus x is the same thing as 1 over 1 minus negative x, and this should look familiar. We know the power series representation of 1 over 1 minus x. Okay, that's just x to the n. So instead of x, it's minus x, so minus x to n, which we can rewrite as minus 1 to the n, x to the n. So if I want the power series representation of ln of 1 plus x, I can just integrate both sides of this. Because remember, we can differentiate and integrate power series. So I integrate this guy over here. We can switch the order of the summation and the integral, remember? So then this minus 1 to the n is just a constant. We're integrating with respect to x. So this is a constant, so we just use its power rule. It'll be x to n plus 1 over n plus 1. Technically, there's a plus c, but if you plug in a value of x, you'll find that c is 0, so I didn't write it there, okay? But this is totally acceptable. Usually, people like to notate it as starting from x to the n, a power series. So we just re-index from n equals 1, all right? And then this is how it could look when you re-index it, okay? So this is the power series representation of ln of 1 plus x. This one, okay? Or this one, doesn't matter. Part B asks for radius of convergence. This is actually really, really easy. Because if you just remember the concept that the radius of convergence doesn't change when you integrate or differentiate a power series. So what's the radius of convergence of this guy, 1 over 1 plus x? It's 1. So therefore, the radius of convergence of this is also 1 because we just integrated this power series. R equals 1. Okay? The interval of convergence could change, the endpoint behavior, but the radius of convergence does not change. So this was very easy, part B. I don't know if they expected it to be this easy, whoever wrote this test, but if you just understood this small concept, piece of cake. Otherwise, you can just use the ratio test on this guy and find that R equals 1 as well. Okay? Next, it says use the first two non-zero terms to approximate ln of 3 over 2, non-zero terms of the power series, okay? So we know that ln 3 over 2 is ln of 1.5, right? So then that's just ln of 1 plus 0.5, 1.5, okay? Or ln of 1 plus half, okay? So the first two non-zero terms of the power series, let's go back to here. That's when n equals 1 and n equals 2. So we would get x minus x squared over 2, okay? Therefore, we can approximate ln of 3 halves, or ln of 1 plus half, to be x equals half, so half minus, it has a half here, and then another half squared from x equals half, and then squaring that. So that's half minus the eighth, which is 3/8. So ln of 1 plus half, we can approximate it as 3/8. Okay, pretty straightforward. Now, part D, we're asked to give an upper bound on the error in the approximation, this 3/8 approximation, using Taylor's inequality, okay? So you got to remember the formulas for Taylor's inequality. It looks something like this, and the m is something like this, okay? So, since this was a second-degree Taylor polynomial, we probably want to take the third derivative of ln of 1 plus x in order to use this guy over here, okay? Second degree Taylor polynomial, we take one more derivative of the original function. Okay, so f is ln of 1 plus x. First derivative is this, second derivative is this, third derivative is this, okay? Now we got to maximize this derivative within a certain constraint of x. What's the constraint? Well, we're going to restrict absolute value x is less than or equal to half, okay? Why do we do that? Well, first of all, it should be x minus a, where a is the center, so a is 0. Okay? Now, it's from the center, how far do we go out? Well, since we're centered at 0 and we're evaluating at half, we just go out to half. Okay, so we're going to restrict absolute value x is less than or equal to half. Okay, so that means x can be between negative half and half, by the way. Okay, so when is f triple prime maximized? When x is between negative half and half. It's when x is negative half, actually, because we'll be dividing by the smallest number. Okay? So that's what I said here. So m is max at f triple prime of minus half, which is 16, okay? So our m is going to be 16, and then we got to maximize this guy as well, okay? So the n is degree Taylor polynomial we used, by the way, so n is 2, so that's why we took the third derivative, n plus 1, okay? And then x cubed is maximized when x is half, okay? Or negative half because it's absolute value, but for simplicity I put half, so half cubed is an eighth. So now let's plug into this formula over here. So the maximum error is our capital M was 16. Our n plus 1 factorial is 3 factorial. And then this guy we maximize to 1/8. Okay? So the answer is 1/3. The maximum error is 1/3, which is, depending on the application, could be a pretty good approximation. I honestly think this is lousy approximation because imagine you have 0.333 error. Depends on how precise you need it. If it's like a very precise amount you need, like for example, if you're titrating something in chem or something, I just thought of that word for some reason, or imagine you're giving a dosage to a patient. If you give 0.3 extra, it could be lethal, right? So it depends on the approximation, but in my opinion, pretty large error actually for a maximum error, okay? And one more thing I'll say on this part. So of course you have to remember these two formulas. The idea is you want to maximize that m and this guy. This is fixed, okay? Why do we want to maximize? As I just said, you don't want to underestimate, or kind of said, I didn't explicitly say, you never want to underestimate error, okay? You always want to overestimate error because for legal reasons, if you underestimate and there's actually more error, you're going to get in trouble. Okay, so that's why you want to overestimate, and then if your error is actually less than what you estimated, that's fine. Okay, of course you don't want to estimate by too much because you have competition as well. If let's say you advertise that your max error is 1/3 and your competition says that their maximum error is 1/4, that's less error that could happen, maximum error. So people would be drawn to your competition then and not buy your product. Okay, so that's just real life applications, but to understand, that's why we maximize these two to overestimate the error. Okay, that's it for this problem. Again, this is a pretty typical problem on Taylor's series itself, finding it, radius of convergence, Taylor polynomial, and then using Taylor's inequality on that Taylor polynomial. All right, so hopefully this was helpful if you needed more understanding of how to approach these problems, and if I explained anything better, hopefully, if I explained anything well, hopefully that was of help to you. I don't know what I'm saying anymore. Okay, please like and subscribe as always if you found this helpful, and hopefully I see you in another video. Bye.